All right. Welcome back, everyone. Next, we will have Aaron from our LED driver product line to share with us how we can add innovative lighting features into your design with our LED drivers and display tools, design tools. Aaron, thanks. Go ahead.
Hello everyone, really nice to join us here in the sharing session. Quick introduction of myself. My name's Aaron Bin, and I'm the product marketing engineer from TI LED driver product line based in Shanghai, China. And before I go into the technical discussion, so I want to also share you some of the fun facts about our LED drivers. So many people are asking, like, LED driver is such a unique product line in the TI analog territory because LED driver will drive the LEDs. And what you see from your eyes, that the effect is good or not can be judged by your eye visualization. So what you see is good is because our LED driver can do your expectations. From our observation of the market, so we have seen 4 different function quadrant of LED drivers application in the real world. So the first quadrant is called the LED animations. So in our previous generation product or our traditional way of implement LED drivers, we are seeing it on the smart speakers or these kinds of gaming equipments like the mechanical keyboards. So these are all the conceptual of the human-machine interfaces. So our RGB LED drivers will have 2 key features for this, is that we will use it to support it animation with a customized design of color mixing for the human-machine interfaces of the concept. And for the driver side, we have the LED driver that can support it analog dimming and PWM dimming via the I2C and SPI interfaces. So from a data point of view, the LED driver, the RGB ones, are like 30% digital and 70% of the analog. So we will have the digital interfaces to communicate it with the MCU, and you can sending the data of the brightness and the color mixing to toggle the LED driver and make him do the animation per your requirement. And from a market standpoint, the LED driver were usually indoors for those smart speakers or the human-machine interfaces, while through the big trend of the vehicle electrifications, we are seeing there's a big demand of the EV charging stations outdoors. So those EV charging stations will have a RGB light bar on the top. So from your observations, you can see the charging station is green, which means someone is not using it. So you can drive your vehicles there and take the charging to charge your cars. While the color is red, possibly someone is using it or the charging station needs some maintenance. So that's how we are seeing those kind of LED animation has become from indoor applications to outdoor applications. So this will generate a result is that the outdoors with the sunlight, we need a larger current output to show larger brightness. And this is the trend we see in the market, is that we are developing higher current output RGB LED drivers. Okay, for the second quadrant, it's called the LED indications. So different from the LED animation that you're doing some fancy lighting controls, the indication is more straightforward. So it's a simple on-off toggling of the output channels. So we have some general pictures here to show that the left one is TLS speakers. The middle one is those servers and the switches that will have the green LEDs and the orange LEDs to show in the working status. The right one will show those panels. So one is for numbers and one is for letters. So if you have those panels, you can see it everywhere, especially in your home appliances, on those like laundry machines. So this is what we see of the LED indications. So for those simple on-off indication, our LED driver will only do the on-off of the output channel controls, and then these mostly targeting to replaces the discrete solutions you're probably building right now with your GPIO of the MCUs or with some parallel resistor to control or limit the current. While compared to those discrete solutions, our LED driver solutions will have higher integrations and more comprehensive diagnostics and LED current control. So that is our values regarding the LED indications. Okay, for the bottom one, the third column is the LED illuminations. So LED illumination and LED backlight are totally different story than the animation and indication above. So the illumination is DC-DC switching regulator, but you're using it to control the current. So we are seeing some typical application like the one in the picture. So our surveillance cameras, those VR, AR headset. So if you're having those infrared sensor within it to do the eyeball detections and IR detections, the right-hand side one is a VSAR or car scanner or digital scanners. Those will using the LED driver to output impulse current and do the flashing applications. So in a general standpoint, the illumination LED driver will using for a wider applications like infrared, RGBW for color, laser, and even ultraviolet LEDs. And one different thing I want to reiterate that is the LED driver for the illumination is generally high efficiency DC-DC switching because you have to accommodate a different kind of V-in and a V-out power stages. So last one is the LED backlight. So this is more like a straightforward applications. So we will have the LED backlight module co-work with the liquid crystal module layers. So anytime you see a screen from like the wristband, 4 to 5 inches usually, the middle ones, those Apple kits, like the phones or the notebooks from like 10 to 14 inches screen, and the right one will be even larger, 30, 40, or even 60 inch screen of the TVs. Those are all the LED backlight targeting territories. So we will have the backlight modules with the LCD panels for a variety of the screen size. And also similar to the illumination, the backlight LED driver will utilize high efficiency DC-DC power stage. Specifically, it will use the boost topologies because when you are inserting a 12 volts or a 20 volts input and then you are about to drive like 10 or 20 LEDs in serial, that will generate a larger to 40 volts of the forward voltage. So this for the LED backlight modules, you probably want to use the boost topologies in terms of the applications. Okay, forget to mention, so if you have any interrupted question, feel free to raise hands and I will pass the microphone to you. Okay, so from the market standpoint to the LED, our TI LED product line investment areas, so we have categorized those our product into 2 major groups. The left one is what we call the general purpose LED drivers. So we understand that the RGB LEDs, those kind of indicators, and those illumination with infrared sensors are basically everywhere in the world. So we want those kind of the devices or our product to be for general purpose, so they can fit into your application, your power density, your kind of design requirement with a wide range of the scope. So under the general purpose LED driver, we have the illumination and RGB LED drivers. While on the right-hand side one, we call it the display power devices, or called DPD. So under this, we not only having the backlight LED driver that for the TV or screen sizes design, we also have the bias power to support the positive and the negative power rail to do the LCD, like the flip-flop. And we also have those LED display drivers, like the picture down below one. You can usually see this kind of large screen commercial for commercial purposes in shopping mall or in like a traffic stations. So those like 1 dot for 1 pixels are for the LED display drivers. So first section in detail today will be the general purpose LED driver. So we're going to introduce the illumination and RGB and those drivers application in real life. More in detail, so we are hoping our LED driver, especially illumination one, can illuminate the whole world with a wide range of the end applications. So for the left one, we call it the constant illuminations. So why it's constant is our LED driver under these end equipment will mostly working in a constant output. So you are not probably changing the output or toggling the output. So we have 6 major of the lighting sectors. The first, the landscape lighting, mostly outdoors, on the walls of the shopping malls or buildings. The commercial lightings, you see those lights on the top of the roof or on the ceilings. Those are our target. The surgical lightings, these are more professionals that for the doctor to do the surgeries. Also our main target. And the right one, stage lighting, photography lightings are more like professional lighting and high power because it requires a very high power density to illuminate the photography or for the stage performances. The last one is the cabinet lightings. So if it usually seen in the oven or in the fridges. So it can provide some illuminator to your home appliances. Some typical end equipment also illustrated here. The IP camera, mostly accommodating different DC-DC switching or buck boost switching. So for the infrared LED driving in those IP camera applications. The middle one is the DLP projectors. So possibly also the one in the room today. So we are using the LED driver co-work with the DLP chip to make the light luminaire compensation. The last one is the printer. So when we are seeing those contact image sensors within the printer, we use the backlight panel to provide it the light source and for the contact image sensor to do the printing and the scanning. The right one is what we call the instant illuminations. So different from constant illumination that we basically just output the same power density at all time. The instant illumination is mostly you are making the driver to flash a high pulse of the impulse current. So it will more tend to be the flashing. So some typical also applications here. The machine vision camera on the manufacturer line, those permit terminals that you use to scan the QR code on your phones, the torchlight, the fire alarm on the walls, the VR, AR wearables that we just talked through, and those camera flash, those are categorized into the instant illumination. Okay. We will have the illumination LED driver roadmap here. So it follows two major logic of the device comparison. The first one is from the x-axis. So the left one will have the least amount of the output power density, while the right-hand side one will have the largest power density. So you can see we have 100 volts as the most that we can support, but we also having driver that can support it larger than 100 volts of the power density. So the first logic is output power density. The second one to categorize those devices are the DC-DC switching. So we have those linear devices like the TPS 92612 and the TPS 92633. So those are very simple, just one channel or 3 channel current thing. So if you inputting a 40 volts to the VN, and it will generate a path through to the V out 40 volts, and the excessive voltage will burn on the LED drivers. So those typical linear applications will be very cost optimized, and you can use it for a wide range of the input voltage. On the right-hand side, we have buck at the bottom and a boost on the top. So those are DC-DC switching, so we are expecting a higher efficiency of those kind of applications. So the hero devices I want to highlight on this page is on the right-hand side one. At the bottom, it is the TPS 92205. It has 2, 3, 4, 5, 4 different variants within this device family. I will go into some of the detailed explanation after. Also on the top, it has the brother devices, the TPS92365. So it's a boost or buck booster topologies, also supporting 4.5 to 65 volts of the input. And it can support a 2 amperes or 4 amperes DC current. We have some very successful story of these devices on the previous applications like the IP camera, like the DLP projectors. We're having those successful stories. Also could share you later after. And one more devices within the blue color is the TPS92201, the one at the left. So it's a low VN buck converter supporting 2.5 to 5.5 input and 1 amperes current output. So it's more likely for the IP camera or video surveillance related equipment. So we are also sampling these new devices. If you are interested, we can have the EVM and also the sample available for you for the evaluations. When we are developing those LED driver, we also want to have a full picture of the collaterals that can help engineers do a quick start of the evaluations, and those collaterals that can help you do the design of the inductors or the output capacitors, especially when those devices are DC-DC switching. So these pages will show how we are designing those collaterals regarding our LED drivers. So for those constant illumination categorized of the LED driver, first on TI's E2E forum, we will all launching a kind of the posted, what we call how to master TPS 92200 within 5 minutes. So for these kind of new devices, we will all launching this forum is that we will want the engineers when evaluating these devices, we want them to master or doing some basic evaluation startup within 5 minutes. When it goes to these advanced or more complex or detailed level of the design, or when you are writing those schematics, we have the TI design available that with more general pictures of these components on the PCB and have those applications. For example, we have the 100 volts dimmable DC-DC LED driver for the daylight harvesting, especially for and with the wireless connectivity reference designs. So those will having a more bigger pictures to help you do the schematic design. Last one is the training videos. The training videos is more from a general start point. So we are trying to understand it. What is the functional block of an LED driver, and what is the what is some of the point or concerns you usually will have when you are designing an LED driver into your system. Okay, this is the new device family just mentioned, the TPS92205 and the TPS92365X family. So very general introduction of this device family is that it's a 2 amperes or 4 amperes non-synchronous multi-topology LED driver supporting up to 65 volts of the input voltage. And the two major advantages of these new devices is that it can support it very high power density of the illumination, like the one picture of the stage lighting I put next to it. And also the second one feature is the excellent dimming performance that we want to achieve and to give benefit on these new devices. Also want to give a very general example of how those like dimming performance can benefit on people's daily life. So we have these new devices, a wing case at those North European customers, especially for those people living in Arctic regions, and they will have the polar nights happening, so they won't have the sunrise and down usually what we have in Asia regions. So the customers are looking to design a LED light that want to mimic the sunrise or stimulate it, the sunrise and down for those kind of peoples. So the sunrise usually take about hours to do the transitions. So it requires the LED driver to do a very smooth of the transition from like 8 o'clock to 10 o'clock and then to like 2 o'clock in the afternoon. So that is our key features or key values within these new devices, is that we we have completed the most tough or difficult requirement regarding the LED dimming in the world. So we have the confidence to resolve any other kinds of the LED toggling within those stage lighting or the surgical lighting, those harsh applications. Before we go into the LED dimming requirements, also want to share some of the informations when we are designing this new chip from the startup. So when we are designing this new chip, we consider the pinout optimizations to make it compatible with a single layer chip on board LED board design. Because usually when the output power density goes up to 50 or 100 volts, the LED board can be really hot, and we have to consider using some exterior mechanical structure to dissipate the heat generated on the LED boards. So when we're designing this new LED driver to accommodate those high power density applications, we want it to support a single layer PCB layout. So when you're designing the LED board, you can use those aluminum or copper materials on the back end of your PCB to efficiently dissipate those heat generated. So you can see we have considered this as a hard requirement when we are designing the pinout optimizations. So regarding the single layer boost for the common cathode LED connection, or the single layer buck for the common anode LED connections, we don't have too much external circuitry around the ICs, and we can see the easy routing between the grounded and the main pad on the ICs to support it, the single layer design of the PCB layout. For the main topic is how the LED driver dim the LEDs, or the dimming method optimizations that we did. So usually for the LEDs, if you wanted to toggle the on-off, we have seen two main ways to do it. The left one is what we call the serial FET dimming, is that you are making a serial FET on the low side between your LEDs to the ground, and you are toggling this power MOSFET within the signal sending from LED driver or possibly sending from MCU. And then the middle one is parallel also power FET across your LED anode and cathode, and the control signal is sending from the driver or the MCU. But these two mechanism or control scheme will have some drawbacks, is that they cannot handle too much current, and it requires external MOSFET to handle the current path through. So it's more like a complex design or additional cost when you're designing the external control of the LED drivers. While what our new product implemented is on the right one is the power FET dimming, is that we will no longer using the external power MOSFET, and we are integrating this into our LED driver. So we are also bringing this new control scheme with some of the major advantages, is that we are improving the higher efficiency for the entire load range of the conditions. So if you are only driving one single LEDs or a long string of the LED strings, it can help you improve the efficiency. And one other thing is that with this high integrations, we are helping reduce the design level complexity and also reduce the cost if you don't want to add an external FET to it. Okay, this page is called the inductive fast dimming. So it's an original TI patent that we just released this year by our R&D engineers and the system engineers. So this is the TI original patent, and the definition of this to improve the LED driver is that the inductive fast dimming enables high-frequency PWM dimming directly by the DC-DC switching converter, but not to the external like parallel or serial FET you just see on the previous slides. And at the same time, we're using this control scheme to improve the accurate of the brightness control and the wide dimming ratios that you wanted the highest brightness and the lowest brightness to have a very clear contrast. For the LED dimming requirements, we have seen two major benefits or advantages with developing this IFD patent. The first one is that we see the wide dimming ratios, so the high bright to low bright contrast is very clear. The second one is the low flickering and possibly the audible noise, which can be caused by a low frequency of the PWM dimming. So we are improving the PWM frequency up to 20 kHz or above to avoid 100% of this flickering issues. So both of these two benefits will lead to one single parameter that you can value or judge a LED driver can do good or not on the dimming is that the minimum PWM on time. So the shorter we can turn on the duty cycle, the more contrast we can have in terms of a low bright to high bright contrast ratio. And so that's the one key values or parameters is that our new devices can handle lower to 200 nanosecond or 0.2 micro PWM minimum on time, especially this number can help in a variety of the end equipment that we have the samples on the right corner. So we have surgical lighting, stage lighting, those home lighting. So we when you are decorate your home, you want to add those light bars or warm or white LEDs on the top of your ceilings. Those can be really nice if you can have the inductive fast dimming technology into it. For the low flickering issues, also it's a very common phenomenon in the surgical stage, photography lighting and machine vision. So imagine that if you are doing a streaming or something and someone is using the iPhones or high-speed 4K camera to take shoot of the photography lighting behind you to do the light compositions, and you definitely don't want those flickering light bars to appear in the pictures, and those watermark, those phenomenons appears on your pictures. So that is our main target to resolve within this IFD new technologies. In addition to the previous pages, we also have the dimming modes selectables. So we have two different pinouts, one taking the PWM dimming pins, and one is the analog dimming pins. So with 2 pins, we have 4 modes of the dimming modes. So you can inserting the PWM signals into the PWM pins and also the signals to the analog dimming pin to achieve what we call the hybrid dimmings. So the hybrid is a combo of the analog dimming and the PWM dimming. So you can see figure 2 is this example of the waveform. So when a PWM duty cycle is at 12.5%. Above than that, we are using the analog, which is internal DAC to do the analog dimming. When the PWM duty cycle you're inserting is smaller than 12.5%, we are automatically switching it to the PWM dimming. This kind of control scheme also helps improves the analog dimming when the output current is really low, for example, 10 microamperes or 5 microamperes. At this level, when you're still using the DAC to do the analog dimming, the linearity can be really bad. So for example, if you wanted to output a 5 milliamperes, probably you will get a 6 or 7 milliamperes, and you want to control this more precisely with the PWM duty cycle to achieve a better linearities. Okay, so I won't go into much detail of the device one pages. So if you having some of that detail specs you want to check with me, also feel free to reach out to me after in the break. Okay. The second sector is the RGB LED driver, as we are having 2 demos on the demo tables. So we are seeing those RGB LED driver has 2 major applications. One is the one on the smart speaker, is the LED animations. You will have a lighter ring circling around or some RGB color breathing. Those are the human-machine interfaces status that can co-work with the human beings at home. Well, the second one is the LED indication. That is more simple on-off toggling controls that you can see those number or letter panels on the laundry machines. So This pages follows the logic. The left side of the LED driver will supported 1 to 12 LED dots, while the right-hand side one, the LP589X, will support 700 to 12K LED dot with one IC design. So you can see the logic here is the increase of LED dots supporting by one IC from the lowest to the highest. So I will highlight two device families today. One is the LP581X that is sampling on the very left-hand side. And the second one is the LP586XT family that in the middle, supporting 18 to 198 LED dots. So these are the two new devices I want to highlight with some technical details today. Okay. The first one is the LP581X family. So we are putting a general picture of the TWS headphones and those kind of equipments that powered by batteries, but also having LED lighting or visualizations on it. So this LP581X device family is a RGB LED driver supporting up to 12 LED dots, and it is integrated with a synchronous boost to accommodate battery-powered products, and it also has the autonomous animation controls to release the bus load on MCUs. So some main benefits for those battery-powered system. The first one is that with our integrated boost converters, we can help maximize battery endurance time with down to 900 microamperes of the operation current on the LED driver and up to 94% of the efficiency when you're doing the boost converter to generate a higher Vout for the LEDs. The second one is that we are optimizing solution cost and size with what we call the time cross multiplexing architecture. Also, we'll have a single one-pager to introduce this. What is the time cross multiplexing architecture? But with this architecture, we're able to fit in this new driver in a very small package. You can see down below, we can fit it into 1.8 times 1.4 DSBGA 12 pins package, especially for those like TWS speakers. It usually don't have enough PCB sizes for the design. This kind of chip can be really helpful when you're designing with a limitation on the PCB sizes. Last one is the free MCU process, real-time processing load with the auto animation controls. Because usually when the LEDs are doing the light ring chasing, it's repeating the same patterns. So when you're coding the C program, you're probably just putting the same patterns within the while loop. So that can causing really massive loaded to your MCU. Communicated on I2C or SPIs. So what we do also on this LED driver chip is that we're doing additional digital circuitry in this IC to help you repeat it the same animation pattern, so you don't have to constantly repeat it, sending the data from MCU to LED driver, and this can also help saving the power. So this page introduces what we call the time cross multiplexing control scheme. So for this traditional multi-channel LED drivers, usually one channel of current sync to control one single LEDs. So how many channel we have will generally for how many LEDs dot we can support it. But with this time cross multiplexing controls, we can using only 4 output channels to support it up to 12 single color LED dots. And how this is accomplished is that we have internal PMOS switching FET integrated into the output pins. So this is a picture showing you how those switching can done. So at the phase 1, the Out0 is pulled up to Vout, and the Out0 is outputting the switching signals, while the Out1, 2, and the 3 are pulled down to the current sync. So the current flow will floating starting from the Vout on the L0, and it will across this the D0, the RGB LED dot, and a downflow to the L1, 2, and 3. So at the phase 1, we are using this output to control to lighten up the D0 RGB LED dot. So same story, at the phase 2, we will pull down the L0 to down below the current sink, while we will pull up the L1. So also constantly switching from phase 3 and phase 4. So since this is a high-speed switching from out 1 and 4, from phase 1 and 4 back again, so it also has a requirement on the PWM frequency that we want to make it higher than 200 Hertz that can be observed by human eyes, and 2K Hertz that can be captured by high-speed cameras. Our LP5812 or 13 devices can handle up to 6K or 24K Hertz of the PWM dimming frequency that can avoid any kind of the flickering issues. For the autonomous animation controls, for traditional way of toggling the brightness or sending the color mixing data, we have the MCU also always working on the I2C bus line to sending data to LED driver. While with this our new feature in this LED driver IC, we only need an initialization from MCU, and it can just get into idle mode without any communication with the LED driver. So how this is essentially done is by the internal digital circuitry that you can configure by the registers. So we are having an animation pattern picture here. So we will have 3 groups of the register. The first group is what we call the APU. So it's an animation pulse unit. So we will use it to determine when you want it to start or end the same animation pattern. The second one is called the AEU, so it's the animation engine unit. So it will determine what kind of the animation, like the example waveform on the right-hand side. You want the green or yellow color to ramp up and ramp down within your customizations. So that is what the AEU, the engine unit, would do. The third one is the playback time, so we call it the PT. So the PT will determine how many times you want to loop the same animation patterns within the design. So with these 3 groups of the register configurations, we have all the abilities for your customizations or design to do whatever the RGBW indicators or animation transitions per your design requirement. By the way, the demo boost on the LED light ring is just accomplished by this LP5813 new devices. Also not going to go through some of the details on the one-pager. So if you do looking forward to design some of those like animations on your end product, or those like light bars on your end products, you can also reach out to me, and we can somehow discuss some technical details within this new device. And another thing that I want to talk through is the matrix driver. That we have a typical picture here as the RGB mechanical keyboard. And why I'm illustrating this is that we're having a new T version family that can support a higher current output. So you can see down below the variant device family. So we have the LP5860, and also we have the LP5860T. So the T here stands for the turbo. So if you have the turbo engines, you will have those 100 milliamperes to support a higher brightness on your design of those matrix LED animation patterns. Also, for these kind of like high integration of the LED dots, supporting especially on those mechanical keyboards, you're looking for 100 or above LED dots. So we're using the time multiplexing control scheme to achieve this kind of a high integrations. But different from the previous devices that I introduced for the TWS speakers. So this one will separate the scanline MOSFET with the current sink on the down below. So this is more likely in a mathematical matrix that we are seeing. So it has X lines and it has Y lines. So similar way of approaching for this time multiplexing controls. At the line 0, we're only turning on the sync 0, and the last one is sync 17. So you can see on the left one, only the first and the last one LEDs will be turning on. So at the line 1, so we're switching from 0 to 1, and we're turning all the sync 0 to sync 17. So basically, we're turning on all the LEDs on the scan line 1. So at this moment, you will see all the LEDs turning on. After, so this is also a high frequency switching from line 0 to line line N, and you are switching back and forth. So same story on the PWM frequency. We definitely want to avoid it, the 200 hertz and 2K hertz of the frequency. So we are making these devices, excuse me, above than 62.5 kHz and in the range of 125 kHz. So this will also avoid the problem of the flickering. From a more professional way of your visualization, the picture, or your calibration, the color. So we're also integrated premium dimming control of these new devices. At the left-hand side, it's the analog dimming. So we are usually using the analog dimming, the internal DAC, to change the current DC current level of the output current. So we have the global 3-bit of the register to control all the color group. So we are putting a picture of the different ambient light here. So you are probably using this register to do the white balance. So you can make all the yellow LEDs really yellow, and it will turn your color into a sunrise, a sunfall. If you are toggling the white balance to really bright, it will turn to the left one that is really white. So this is what we do for the ambient light control with the white balance. The color temperature setting is the second one we are controlling regarding the CIE 1931, the color legend graph. So this is more for very professional way of designing the RGB color that you probably wanted to maintain the same color temperature when the LEDs are using for a very long time. So if you're using the LEDs for like 5 years or 10 years, the LED itself can be yellowish after a long time of use. Well, you can using this type of register to adjust it, the color balance and the temperature. The last one is the dot correction. So especially if we are designing those single dot LED control on the keyboard. So if you press a key, a corresponding color will appear. The dot correction function is especially important to support this kind of the design. The right-hand side is the PWM dimming. So we are usually using the PWM dimming or the duty cycle control to do the control of the brightness. So we have the 16-bit of the PWM dimming, which is the highest resolution within the industrial. So competitors can usually do 12 or 13, but our 16 bits is the top resolution within the brightness control. So with this 16-bit of resolution, so you can toggling the current from down to 0.1 microamperes up to like 50 microamperes with more steps in between. So that gives you a very smooth color transitions if you're toggling the PWM duty cycle. Okay. Last one page about this new devices is that sometimes we are seeing the data transition from the MCU to the LED driver has a delay on the signals. So on the left-hand side one for these LED indication, for example, if you wanted to change one single dot indicator from green to orange, it's a one time of the data transmissions. While on the right-hand side one, the LED animations, so the animation is possibly transiting from frames to frame. And then one frame will consist about like 100 or even like 1,000 numbers of LED dots. And we want the dots to upgrade it within frame, but not within dots. So we want to reduce the delay on the transmission of the I2C bus load. So we have those VSync, so synchronous pin available on this driver. So you can pull it down and wait until all the frame data enter the SRAM on the LED driver and then release it to the second PCIe of the SRAM. So you can see we have a visualization here showing the Mario animation the transition. So we updated the animation frame by frame instead of like LED dot by dot. Also not going through some of those detailed single device one pages, but this is what we also see in some great values within the industry. And if you have some interest or details you want to check, also feel free to reach out. Okay. The second section today will be about the display power drivers. So it's more about the screen sizes design or the liquid crystal design that we have. But I don't think we have too much time today to go into the details that we just illustrated for the illumination and RGB. But I will also show the roadmap and how our new devices development and those logistics into it. Okay, so this is a general or global trend we see, especially on the display technologies. So we have the separate groups for them. One is the traditional LCD, so the liquid crystal display. The one most advanced can be OLED. The right-hand side one is the mini or micro LEDs. That gives you the highest contrast ratio and the display qualities. So for the traditional one of the global dimming, so the first picture, the global dimming, the edge backlit, you can see it is widely implemented on the laptops or your TVs, especially those laptops that has a thin black layer on the top. So you will understand it that there is a very thin PCB on those black layers, under those black layers that basically do the LED backlighting. So you can see the picture in one is that the light will be sprayed from the edge to the middle. So we also call it the edge backlight. It's a very mature technologies, but it has the drawback on the contrast ratio is that it's not very good. But since it's a very well-developed technologies, the lifetime and the product complexity, it has its advantages on this global dimming technologies. The second one belongs to the liquid crystal, is the local dimming, also what we call the direct backlight. So different from what we're spraying the light from the edge of the backlight modules, we are having those backlight modules directly behind the pictures or the liquid crystal panels. So you can see in the pictures for those night picture, the moon, you want to give some illuminator to the moon. You just need to illuminate it, those specific backlight modules at the back end. So it's not spraying the light bars from the edges. So disadvantages is that it's causing the contrast ratio to improve, and this is also a liquid crystal technology, so the lifetime is pretty good, and we are improving the number of LED driver IC on it, so it has a slightly more complexity on the productions. For our TI backlight LED driver portfolios, we have a very well developed and new devices, especially targeting for the local dimming. So this is a trend we see in the market, especially for the display market, that we're improving the display quality within this local dimming technologies. For the right two one, the OLED and the mini or micro LEDs, those are all pixel dimming. So it will not do the liquid crystal flip-flop like the LCD display. So it's more likely to be one LED dot for one pixel. So if you want a 4K resolution, you needed that kind of LED dot to support your display qualities. So for these two columns, we also have the solutions to support the bias powers and also the commercials for the TVs. And these will, since they are the direct display, it will have the highest contrast ratio if you are trying to see the visualizations. But the OLED and the mini micro LEDs also having its kind of drawbacks or shortcomings is that they are not well tested by the market, and they're still in like early or middle development stage. So even these give you the ultimate visualization or display qualities. So these are still not the major trend in the current display market. Okay, this page shows only the automotive backlight LED drivers. Since the EV cars are now getting more and more popular, the infotainment are definitely one of its design spec. So we have the global dimming on the left and the local dimming on the right, or well designed and have a full portfolio to support it. There's automotive infotainment LED backlight modules that you can see. We have the new device family that I want to highlight on this page is the TLC696X1. So on the very top right corner. So it is the newest local dimming LED backlight devices that we have developed, especially to improve those automotive infotainment display qualities that you currently see in contrast to the global dimming technologies. While on the commercial side, it's more for television or PC gaming monitors. We also having those very good portfolios or devices that can handle the design specs. So the top half one are for the multi-channels. You can see the y-axis is increasing from 1 channel to 3, 6, and 8 channels. So the more channel numbers, the larger screen sizes you can have to design with your screen. And on the x-axis is the increasing of the output current or the powers. So if you want to look into design a higher brightness on the TV designs, so definitely 100 or 200 milliamperes are the target. I want to highlight 2 new devices that we are still under development right now. Those are in red. So one is the TPS923388. It has a unique 3-level DC-DC with ultra high efficiency. So you can see the top left corner. So it has a blue 3 around to it. So this is also the first devices within the backlight module industry that we are designing a 3-level DC-DC. So it's not a 2 low side, high side MOSFET integrated in it. It's a 4 MOSFET integrated solutions that we're hoping to improving the boost efficiency up to 94 or 95%. And it can benefit on your applications on the laptop or those pad. Those can extend the battery lifetime with about 15 or 20%. And the other one in red is the TPS92361 at the right top, right bottom corner. So we are refreshing our traditional TPS 611 series that usually is a single channel for lower than 10 inches of the screen design that is getting very popular on the market. So we are also having planned to refresh those traditional devices within asynchronous the boost topologies. So for those 611 out part, it's a boost that still has a power diode on the external circuitry, so the efficiency needs some improvement to it. Also, so that's why we are releasing the TPS 92361 as the next generation to them to have some major advantages. That's all I have today for the introduction of the LED driver side. So we have a more detailed introduction on the RGB illumination and some general levels on the backlight modules and those in commercial TVs and automotive infotainment. So do you have any questions? Okay, thank you.